A common use of pooled data is to evaluate the impact of an event or policy change. For example, you may want to investigate the effect of a new garbage incinerator on house prices. The data involved would consist of two cross-sections, one from 2010, before the incinerator's construction, and the other from 2020, after its construction. A naive analysis would compare the average house prices of properties near the incinerator with those farther away. This can be done by estimating a simple regression using data from only 2020. For each house I, price is the price in dollars. Near is a dummy variable that equals 1 if the house is near the incinerator, defined as being within a specified distance, and 0 otherwise, and epsilon is the error. This is the estimated regression. The results tell us that in 2020, houses near the incinerator are on average $30,688 cheaper than those farther away. What's wrong with attributing the entire $30,688 difference in price to the impact of the incinerator? There could have been a price differential between the two locations even before the incinerator was built. The government may have chosen to build the incinerator in a poorer neighborhood where house prices were already lower. Thus, the observed difference in house prices after the construction of the incinerator could reflect both the impact of the incinerator and the pre-existing price disparity between the areas. To accurately assess the effect of the incinerator, we need to compare the difference in house prices both before and after its construction. To examine the difference in house prices before the construction of the incinerator, we estimate a simple regression using data from only 2010. This shows that house prices near the incinerator were already $18,824 lower. This confirms our intuition that the $30,688 difference observed after the construction of the incinerator reflects both the impact of the incinerator and the initial $18,824 price difference. Therefore, we need to estimate the change in price differences observed before and after the construction of the incinerator. This is the estimation of the impact, the true amount by which the incinerator decreased the house's price near it. We call this the difference in differences estimator because it measures the difference between two changes, one in house prices before the construction of the incinerator, and the other in house prices after the construction. Overall, we first regressed price on the near dummy using only data from before the construction of the incinerator. Then, we estimated the same regression using only data from after the construction. The difference between these coefficients is the difference in differences estimate. One way to obtain the difference in differences estimator and its associated standard error directly is to use a single regression model. For each house I in year T, price is the price in dollars. After is a dummy variable that equals 1 if the year is after the incinerator has been built and 0 otherwise. Near is a dummy variable that equals 1 if the house is near the incinerator and 0 otherwise, and epsilon is the error. We introduce an interaction between the near and after dummy variables. We have two groups, treatment and control. The treatment group consists of houses near the incinerator, while the control group consists of houses farther from the incinerator. The treatment refers to the construction of the incinerator. For each group, we observe house prices both before and after the treatment. For the control group before the treatment, the near dummy variable will be equal to 0, the after dummy variable will be equal to 0, and the interaction term will be equal to 0, so the expected house price will be equal to beta O. For the treatment group before the treatment, the after dummy variable will be equal to 0, the near dummy variable will be equal to 1, and the interaction term will be equal to 0, so the expected house price will be equal to beta O plus beta 1. Beta 1 is the difference in expected house prices between the treatment and control groups before the treatment. Overall, the difference in expected house prices between the treatment and control groups before the treatment is equal to beta 1. For the control group after the treatment, the near dummy variable will be equal to 0, the after dummy variable will be equal to 1, and the interaction term will be equal to 0, so the expected house price will be equal to beta O plus delta O. Delta O is the difference in expected house prices for the control group before and after the treatment. For the treatment group after the treatment, the near dummy variable will be equal to 1, the after dummy variable will be equal to 1, and the interaction term will be equal to 1, so the expected house price will be equal to beta O plus beta 1 plus delta 1. Delta 1 is the effect of being in the treatment group and experiencing the treatment. Overall, the difference in expected house prices between the treatment and control groups after the treatment is equal to beta 1 plus delta 1. For the control group, the difference in house prices before and after the treatment is delta O. For the treatment group, the difference in house prices before and after the treatment is delta O plus delta 1. The change in the difference in house prices between the control and treatment groups before and after the treatment is the difference in differences, DID, estimator, which is delta 1. The assumption in a DID model is that in the absence of the treatment, the outcome for the treatment group would have followed a path parallel to that of the control group. This is known as the parallel trends assumption. Therefore, we can attribute any change in the outcome for the treatment group after the treatment solely to the treatment itself and not to any other factor. For example, imagine a scenario where the treatment didn't occur. We would observe house prices for both the treatment and control groups moving in parallel over time. Initially, the treatment group may have systematically lower prices than the control group, possibly because the government chose a poorer neighborhood with lower house prices for the site of the incinerator. Over time, this price difference between the treatment and control groups would persist, and their house prices would continue to follow parallel paths. If the parallel trends assumption is violated and the treatment and control groups were initially on diverging trends, such that even without the treatment, house prices for the control group were increasing faster than for the treatment group, then after the treatment, any drop in house prices for the treatment group could reflect both the treatment effect and the underlying divergence in trends between the two groups. This would result in a biased estimate of the treatment effect. When can we use a DID estimator to estimate the effect of a policy? There should be an exogenous event, such as a policy change, affecting a treatment group while a control group remains unaffected by the change. Before and after comparisons can arise from natural experiments, which are naturally occurring events leading to random assignment into treatment and control groups. The treatment group consisted of houses near the incinerator, which already had lower prices before construction. The government likely chose an area with lower house prices for the incinerator site, indicating that the assignment of treatment is not random. Random assignment implies no initial differences between the treatment and control groups before the treatment. Because the assignment is not random, we need to control for systematic differences between the treatment and control groups. For more lessons on econometrics, visit alphas&betas.org.